When it comes to finding planets outside our solar system, no space mission to date can beat NASA's Kepler. In 5 years, it has found more than 1,000 confirmed exoplanets, with thousands more awaiting confirmation. Kepler finds exoplanets by carefully watching starlight, looking for slight dips in brightness as a planet passes in front of, or transits, its star. This technique, called time series transit photometry, is most effective for large planets in close orbits. This both maximizes the light loss during a given transit and the number of transits we observe. But how far can astronomers go with this technique? Can we find a twin of Earth? Or even identify whether a planet has moons? With 2 transit photometry missions on the horizon, NASA's TESS and ESA's Plato, some astronomers have examined the limits of this technique with surprising results.
For our study, Michael Hipke and I combined the knowledge or the lesson learned from Kepler with what we know about the future missions like TESS and Plato. And we ask ourselves the question, what would we be able to see if we put these observatories outside our solar system and observe our solar system? And the results are that we probably won't be able to see Mars or Mercury, but everything else in our solar system, we definitely get a solid detection of Earth, solid detection of Venus, also of the outer planets. We might even be able to see ring structures like the one around Saturn and maybe even moons, Jupiter's moons.
In another study, they pushed Kepler to the limit by cleverly combining almost all extrasolar planet data collected by the telescope using an understanding of orbital mechanics.
For example, Jupiter has so-called Trojan asteroids that collect in 2 specific areas on its orbit, pretty symmetrically to its orbit. And in the study that we did on the Kepler data, where we added up all the phase curves of all 4,000 planets in the Kepler dataset, we were even able to see signatures of asteroids in extrasolar systems. And with the future missions, we might even be able to find that in individual systems and not just by putting all the data together. We wanted to figure out what the ultimate limit is that we can do photometry with, and it turns out with the next generation of instruments we already hitting the technical limit and are mostly limited by the variation of the host stars themselves, by the huge noise that's coming from the host stars.
The way to push down this noise is by observing stars for longer periods to improve models of the star's behavior, allowing astronomers to tease out the smallest transits. The work of Hipke and Angerhausen shows that future missions will be able to detect Earth-sized planets orbiting Sun-like stars at distances that would allow liquid water. These systems will become prime targets for more detailed study using other missions, such as NASA's James Webb Space Telescope. Will we find a copy of our solar system? How common are habitable worlds, and particularly twins of Earth? The thousands of exoplanets to be discovered by TESS and Plato will go a long way to providing answers.